Thank you very much. I wanted to thank Gabriel for inviting, but I'll have to do it whenever I see him next. He's not here. This is a very general talk. This is not as technical as some of the talks have been. It's more about a little bit in the philosophy than the actual details. I want to talk about functional data, and I want to make a connection with shape analysis. This is the main message. In statistics, one of the fastest growing areas is called functional data analysis. If you go to a statistics meeting, there are always now a large number of sessions on dealing with functional data. The main message I have today is that instead of working with functions in generality the way people do, in some cases it's advantageous to look at the shapes of the functions for all kinds of statistical analysis. At the very least, one should separate the shape variables and the non-shape variables. And more generally, just in addition to doing this, more generally, there are these two sets of people who do traditional shape analysis, and there are statisticians who do functional data analysis, and these two people generally stay away from each other. There is a great need to do this together, and it leads to tools that are very useful, broadly applicable. So that's the general message. But I want to start, maybe I have to stand up a little. I want to start with little sort of looking back historically. Shape analysis, a lot of people have worked in this area. I have worked in shape analysis for at least 15 years. A lot of progress has been made. I mean, we always debate about your method versus our method, but as a group, this community has made great progress. And one of the reasons for that happening is the collaboration, the consortium between geometry and statistics. There are several important groups who have made big contributions, and we look at those groups. Jim is here, so I can talk about North Carolina group. They have mathematicians, Jim, and statistician, Steve Marin, and computer scientist, Steve Pfizer, all working together closely. And that's really one of the reasons for success in this area. In terms of shape analysis, a lot of different objects have been studied. People start from a computer vision point of view, shape analysis of contours. That was an important starting point. Curves in Euclidean spaces, shape analysis of three-dimensional objects in computer graphics, medical imaging. Stephanie just gave a talk on shape analysis of curves on manifolds. She was talking about longitudinal shape data that essentially shapes, there are curves or trajectories on manifolds. A lot of work has been done on that. More branching out of beyond these traditional well-defined domains, tree-like structures, how, for example, neuron morphology, how to compare shapes and modeling and testing and analysis of shapes which are more diverse and more complex. And lots of different application domains are driving these. A lot of this, very true to the name of this workshop here, it's imaging is in the title of the workshop. A lot of these applications come from imaging data. But, and that's what I used to advocate. All my life, I always told my statistics audience that imaging data is a very important source of data. We should look at it. But I'm going to play the reverse role. I'm trying to say that there is much larger community outside imaging data which can benefit from these techniques in shape analysis. I want to summarize what people do typically in shape analysis. At the very least, one wants to come up with the way of comparing shapes. Some metric which says, here is a quantification of how different two shapes are. So one develops shape metrics. We talk about shape deformations, optimal deformations, how to take one shape and deform it into another shape. If you're taking a Riemannian approach or a metric-based approach, then you talk about geodesic paths between shapes. Once you have these basic tools, you can start doing summary statistics. Using metrics, you can talk about average quantities. So for example, in Stephanie's work, she talked about mean trajectory. If you have a metric on that space, you can estimate a mean trajectory. You can do sample covariances and principal component analysis. When we have lots of shapes, we want to extract what are the main patterns of variability in the data. And so principal components are a useful tool in that. One can go further, not only just summarizing, but actual testing of shapes. So for example, analysis of variance, two-sample test. The classical tests for testing populations in statistics can be brought over to shape spaces and have been brought over to shape spaces. I just want to mention a few of the applications that our group has developed in the past. Some very interesting applications of these ideas. So for example, we looked at mitochondria morphology. So they're asking the question that in a certain muscle tissue, they look at the cellular level. In fact, they go inside the cell and they look at the mitochondria. And they say that if you are exercising, if you have a physically active life, does it affect the morphology at the mitochondrial level? So it's a very deep, interesting biological question. Of course, if it has an effect, it will inspire all of us to actually be active. And so this was one of the earliest results we have with these collaborators on showing, using shape analysis technique, that there is a statistically significant difference between the populations of mice which were sedentary and which were active. Shape analysis of shape estimation and analysis of 3D chromosomes from single cell or multiple cell is a very important active area of research. We have some work in that. Brain functional connectivity using fMRI data. One talks about connectivity about different parts of the brain, and then as a time series, it becomes a trajectory on the space of covariance matrices. One is interested in classifying what task is a human being performing by looking at the connectivity patterns changing over time. Subcortical morphology, there's a lot of work in France, in other places, on quantifying cognitive disorders based on the structural changes in morphology. YouTube videos, this video is going to go on YouTube, and we can take this video and extract features and form these representation in a covariance space they call covariance trajectories, and one can do classification of, so there are these humongous data sets with thousands and thousands of videos, and people are interested in classifying what activity is being performed. Somebody is celebrating birthday, somebody is cooking something, so that sort of thing. This very diverse video, so this has been quite successful. Neuron morphology, and so on and so forth. So there are a lot of his past work. I just wanted to mention, if some of you are interested in talking about these applications, this is somewhat looking back. This talk is about functional data analysis. So mathematicians, of course, study function analysis as a standard topic in their graduate curriculum, but functional data analysis as a statistical tool was developed by, at least the name was coined by people like Jim Ramsey and Bernie Silverman. In somewhere in the 80s, they have a very famous textbook on introduction to functional data analysis. The idea is to do data analysis or statistics where the quantities of interest are some functions. So some domain D, where D could be just a unit interval, for a simple example, unit square, or some other domain. The range could be just a real number, or it could even be some manifold value. I will try to keep it simple with studying real valued functions. And so with such data, where the data items are these functions, one wants to be able to do some modeling and inference for such variables. And so typically these functions are element of some Hilbert space, and one uses the Hilbert structure to, for example, come up with an orthonormal basis, to cut down the dimension from infinite to finite by taking some truncated basis and so on. As I mentioned, it's one of the fastest growing areas. It's amazing how many new people are publishing and getting involved in it. Certainly not the new generation is heavily engaged in this. And one of the reasons is, where is functional data? Well, anywhere where you have time. Anything with time is functional data. People used to call it time series, where you had discrete times. You would write it as a model evolving over time, but one can think of it as a continuous path, and it's much more natural to think of it as a function data. What does one do in functional data analysis? Very similar to what people do in shape analysis. You want to summarize the given data. You have your given functions. You want to study what are the principal modes of variability. You model the observations of these functions as some kind of a signal plus noise, write down estimation theory. You have some hypothesis, you develop these two sample tests, k-sample tests, analysis of variance. A lot of these functional predictors are being used to predict some quantities of interest in regression models. So functional regression models are quite active area of research, and these functions are being used to do this. So for example, one wants to look at the shapes as functions and predict the extent of a disease. So that would be a classical regression problem. So what is the key idea here? The foundation of this, the way things stand in the community, functional data analysis, is the choice of metric. So most of the literature uses the most natural, the idea that comes from the elementary classes in this area is L2 norm. So that's the metric structure one imposes on the space. It's a Hilbert structure, so it has inner product, it has norm, and you can do the classical statistics based on this imposition. What is the problem with that? The problem with that is sometimes the results are not as intuitive as you would like. So here is a simple example. I have three functions here, three scalar functions on 0, 1. There is red, blue, and magenta if the projector is doing its job. And we are just computing the pairwise L2 norms, the pairwise standard L2 norms. And it turns out, if you look at these numbers, the distance between the red and magenta is smaller than the distance between red and blue. So there are two types of reactions possible. One, they say it doesn't make sense. Other, he says, yeah, it's fine. That's what it should be. But it's clear that in applications, when we have data where the peaks and valleys in the functions have some interpretations, then we want red and blue to be closer to each other because they have similar structure, if your data has structure. But L2 norm will not do that. In fact, many of these norms will not do that. And so similarly, this case, that red has a smaller norm than this constant function, than this blue curve. Okay? And the issue is that there is a misalignment. There is a shift. People call it the phase variability. So if your data has phase variability, even a small amount of phase variability can completely change your downstream analysis. If you're trying to distinguish it between two classes, diseased and non-diseased, or the differences between the two classes may be smaller than the error introduced by these small shifts. This variability, just by these examples, can overwhelm your data analysis. Okay? Some more examples of what are the consequences of it. So under the L2 norm, if I want to just compute a simple average of the functions, if I have a number of functions here, and they're all bimodal, but their peaks are all shifted. There is phase variability in the data. So if I take the standard average based on the L2 norm, I get an average which has multiple modes. So I have lots of bimodal functions, but their average is not bimodal, is not a good representative. Similarly, if I try to characterize the variations, then the variation does not look normal, does not look natural. Continuing this idea further, maybe I'm taking it a little too far, but I have a set of functions. They are all shifts. They are all time warpings of each other. So they have exactly the same form, but they're just shifted in peaks. So I compute their average. Well, this is what average looks like. But if I look at the principal directions, the principal direction of variability, so there is a mean, and one of them is in the plus direction of the principal component, first principal component, other is the negative direction. So the difference between going along the principal component, you are actually changing the heights. Even though the variability in the data was horizontal, phase variability, the principal components under the L2 norm, the way we are doing, is showing vertical variability, vertical variation. So we are capturing something which is not in the data. Okay? And then, of course, one can look at the principal scores and so on, and it's easy to convince that's not giving us the structure we want. Okay? What is the real issue? What is the underlying issue in the choice of this metric? The choice of L2 norm, if you look at the L2 norm, it's calculated like this. So F1 of t is being compared with F2 of t for the same t. In other words, if I'm trying to compare these two functions, it's always measuring the vertical differences. It assumes vertical registration, just by definition. Okay? And if I use this registration, vertical registration, to interpolate between these two functions, I essentially kill one peak and I create one peak. And somewhere halfway point, I have functions with two peaks. Okay? On the other hand, it would be more natural if, rather than looking at the functions just with vertical registration, but to focus on the shape of the function and try to do registration which is somewhat geometrically more meaningful. Match peaks with peaks and valleys with valleys. And use that registration as a metric or as an interpolation between the function. It is more natural, it will preserve the geometric structures and perhaps do something more. Okay? So this is the goal. The goal is to incorporate this problem of registration in the analysis, in the metric for functional data. So this is the next question. How can we decompose, given any two functions, how can we decompose the differences? And this forces us to think about not just the functions as themselves, but the shapes of the functions. Okay? So I want to talk about the notion of shapes. There are several ways one can do that. So if I have functions, how do they differ? They differ in many ways. They can differ in different number of modes. They have different numbers of peaks and valleys. They may have different heights at these modes. The peaks are taller and less taller. And also the placement, where they are placed. Okay? Sometimes when we talk about shapes, we abstract the shape to be just the number of modes. Let's say I call all the bimodal functions to have the same shape as an abstract quantity. Okay? One does little bit more than that, but just to get introduced. So just shape equals the number of modes. Okay? It just relates to. Or sometimes you say, not only I care about the number of modes, I care about the heights of the mode. So heights of mode also are part of the description of the shape. Okay? So in this plot, all the functions are bimodal. They have different heights and different locations, but we call them the same shape. Because here, my notion of shape is just the number of modes. But here, I include modes plus heights. So because the heights have to be kept constant, the modes are constant, the heights are constant. And the only thing is the location of the modes are changing. So we call, in this context, we call these shapes, these curves, as having the same shape class. Okay? So there are different concepts of shapes depending upon the application, but the location of the peaks, that's usually left out as a non-shape variable. It's usually that's not included in what I call shape. It's a nuisance variable from the perspective of the shape. And from the perspective of shape analysis, we want to separate this nuisance variability, this phase variability, from the height variability. And how does one do that? One uses the action of a diffeomorphism group. So you have some space of function, and there are several actions possible. Depending upon the application, one uses different ones. So the first and the simplest one is simply composition, time warping. You have a function, and gamma is just warping the domain. People call it time warping. It's just moving the peaks horizontally left and right. Okay? So I have a function in blue, and I apply these two different warping functions, and I get these corresponding warped functions. And in this group action, the number and the heights of modes are preserved, but area below the curve or the norm of the curve and so on, so they can change. Okay? There is another action possible where, in addition to just the composition, I can multiply by the determinant of the Jacobian, and just by definition, one can see that this is an area preserving transformation. This is the kind of transformation one uses when you are working with, let's say, probability densities, because you want the area below the curve to remain constant. And so then one can do the time warping, but with these Jacobians. But this can actually change the modes. So this group action can actually change the shape. So if you're interested in shapes of curves, this is not a group action. There is a third one where one uses the square root of determinant, and the beauty of that particular group action is that it preserves the L2 norm. You can take a function and you can apply this group action, and it preserves the L2 norm. So in some context, if that is of importance, for some reason you're interested in preserving the norm, then that's a good action. But again, this action also does not preserve shapes. Since we are interested in shapes, we will resort to the first one I mentioned, which simply moves the peaks left and right. So I've given these two functions, as I showed earlier. My goal is to find a transformation which will decompose the difference between these two functions into a horizontal variability and vertical variability. In other words, I want to take a time warping function gamma, and I want to time warp this blue into this magenta color, so that after I'm done that, the only variability left is vertical. So time warping is the horizontal variability. I align the peaks and valleys as much as I can. Whatever is left is the vertical, and we'll call that the shape variability. How should one do that? There are many ways of doing it. This is just one slide about how we do it. there is a notion of a square root velocity function. One starts with the original function f, computes a new function q, and if you time warp the original function, the warping on the SRVF space is this norm-preserving. So this diagram in some ways commutes. One can start with f, time warp it, and compute SRVF, or compute SRVF and then do this group action, and it's the same thing. The nice thing about using SRVFs is that a well-known distance, which has nice invariance properties, and the invariance is coming up here, is that distance becomes the L2 norm between the SRVFs of two functions. So if I want to compute this so-called Fisher-Rao distance between two functions, I go into the SRVF space and just compute the L2 norm, and that's exactly the Fisher-Rao distance. And what is nice about Fisher-Rao distance is that if I take two functions and I do the same warping, before the warping and after the warping, the L2 norm is preserved. This is what I meant by the invariance of the Fisher-Rao metric. It helps us preserve certain nice properties and allows us to set up a registration problem, which is, I will just talk about this approximate one. If I have to register two functions f1 and f2, I compute their SRVFs, q1 and q2. I fix q1, and I do all possible time warpings in this group action of the second one, and the best one comes out to be the one that aligns the peaks of f1 and f2. Okay? So it's a very simple story. There is a dynamic programming algorithm. Over the years, people have developed many more optimal, faster, efficient products. So what it does is, once you have found the optimal alignment, the difference that is left between the SRVFs after alignment, the so-called vertical variability, it measures the difference between the shapes of the two functions. If I'm interested in measuring the shapes of any two functions, I align them in this way and then compute this quantity. So that's called the shape metric. One can also measure the phase metric, how much work was done in doing the alignment. And so whatever was the optimal warping, how far is it from identity? How much deformation did you do? So one can call it the phase metric. One can extend this idea to multiple functions. This is a very simple code. It's about 10-line code, and it works rather fast and rather well. This is the input to the code, a number of functions, no other parameter. There's no tuning needed. And what it outputs are the aligned functions. They have been all time warped to do the alignment. So in some ways, they represent the shapes. And it also gives you the phase component, the time warping that was done in aligning. So this is a tool for taking the original functional data and breaking it up into the shape part and the non-shape part, the phase part. Okay. So some examples of that. There is a study we have ongoing based on electricity consumption in Tallahassee, where I live. It actually turned out later on, I found out my house is one of the data points. I didn't know that earlier. But these are the daily profiles. It's on 0 to 1. It's a 24-hour consumption profile, electricity profile of many, many households in the month of January in a certain neighborhood. And if you just try to do the L2 average and try to find out some pattern, because the peaks and valleys, the consumption profiles don't line up, you don't get a good structure. But when you start looking at the shapes of these functions, which means you align them and then start computing average, you see very distinct patterns of consumption. The electricity company is very interested in predicting what is the electricity profile, because as we know, electricity is one of those resources that cannot be stored. It has to be consumed at the moment it's generated. And so they have to know these patterns of consumption, and you don't see much pattern if you work with the original functional data analysis framework. But if you start looking at the shapes of the functions, then you see something more interesting. Another project we are looking at, something very similar. This is, they pluck out the hair and they put it on the microscope, and they actually look at the color, the grayscale color along the hair. So it's about 6 centimeter. The first half centimeter is used to clamp in the microscope. And these are grayscale values of the points along the hair. To us, we may not be able to see it, but as hair is coming out of the scalp, it is carrying a signature about your situations, and it's a barcode of what you went through. And so they are interested in studying these barcodes. So they are different subjects, different parts of the skull from which they are doing it. So once again, we looked at the averages of many such data from the same person or different person. If you just do simple averaging, you get this red curve. But if you do the averaging with alignment, you get this blue curve. And if you zoom in, this is a zoom in from 1 to 2 centimeter area, you can see that there are actually clear peaks and valleys which will be lost if you don't focus on the shape. And the effort we are trying to do right now is you measure that, they say that it's about a centimeter per month, so you look at 1 centimeter, and if we count, we are getting approximately 26, 27 peaks on average, and we're trying to correlate it with 30 diurnal cycle, 30 days in a month, approximately. And so are these daily hormonal patterns, peaks and valleys, which are coming out as a barcode in your hair. So some interesting data set, there's a lot of data set like this. Okay. Talking about shapes, there is an important application area in functional data analysis, which is regression. You want to use functions as predictors to predict some scalar quantities. So it's a standard regression model. One of those standard models is so-called functional linear regression and wrapped around with a single index, where you have the linear term, you have beta, which is a coefficient of regression, but it's actually also a function. You have the standard L2 inner product, and then H is a scalar function, which could be nonlinear. So this is a standard single index model for linear regression. Okay. But in this case, one is using the shape of F, because it's using the full L2 metric. Oh, sorry. It's using full of F, not the shape of F. And in many cases, in the regression problem, we are interested in using the shape of the function as a predictor, not the function itself. So in other words, the placement of peaks may not be that relevant. The heights and the number of peaks, which represent the shape, may be more relevant. And so we modify this model by taking this standard L2 inner product and performing an inner product which takes an infimum over all time warping. So you align it with the coefficient of regression and feed that in a single index model. Okay. So just as an application of this thing, this is more for humor than anything else, very preliminary. We are looking at the citation profiles of prominent researchers. This Google index, you have the number of citations per year. And so you have this citation profile, and the goal is to use this profile to predict some performance index. So for example, H index or something, some scalar number. Somebody will come up with what index should one predict. So these are the predictors, the functions. H indices of these people are the response, and we want to write down a regression model to do it. I will just quickly say what we have, a lot more details to it. But if you use just the citation profiles, just the function as themselves, without worrying about shape, a linear model gives us this R square, and the nonlinear model, single index model. And when we start looking at the shapes, that means we start time warping them to align them, then you start getting some improvement. The shape is, so if you have increasing shape, then it doesn't matter whether you peaked early or peaked later, at least you have shape for the purposes of H indices. Of course, people say, why don't you do neural networks? But that requires a lot of data. To get a lot of data for a lot of researchers from Google is a complicated story, but we have it now. And so hopefully in some stage we'll compare these things. It's a fun project. Hopefully it will not upset or anybody. Okay. The other problem that comes in functional data analysis is estimating functions. So you are given data, you are given discrete points, and you have to fit a function. It's a problem of curve fitting. That's what it is. Okay. And the usual least squares problem, you are given at time ti, you are given the heights yi, and you try to find a function which will do that. And of course, this by itself is ill-defined, so you put some penalty terms. In practice, you represent the unknown function with a basis, and you convert it into a linear regression problem, and you solve for it. That's a standard story. Now, suppose I tell you that I know about the shape of this function. So suppose for electricity profile, we have studied profiles of households, and we know their shapes look like something. And now I get a new data set, and I want to enforce that shape constraint on a new data set. As a simple example, I want to say, here is a data set, fit a curve in a least square sense, but make sure it's bimodal. Okay? So that's the kind of problem. And so the way one does it is we pick up an element, any element from the correct shape class, and explore that shape class by applying all possible time warpings, all possible group actions. So this particular action preserves the heights, but one can make heights of the modes as an additional variable, additional vector of variables, and search over this. So this is one of the first efforts in the area of estimating functions, curve fitting, under shape constraints, that you know what shape you're looking for, broadly speaking. And that makes sometimes the problem much more well posed, as opposed to just unconstrained function estimation. The actual optimization, here is an optimization over this time warping function. The way it is done, it's not so critical. It's a level of detail. It's a nonlinear space, so one has to flatten the manifold locally and do these things. Here are some examples, just simple simulated data. 1D example, we sample these red dots according to an equation for a function plus some noise. And the only thing we know is that it's a unimodal function. So we are given these red dots. The black curve was the original curve. And using the red dot, we are fitting a function, which is this dotted blue line, under the constraint that is unimodal. Okay? If we don't have that constraint, well, we'll have to use one technique or another and see something. And same here. Here it's a bimodal function. There is two modes. And the black curve was the true curve. And with this noisy data, we are trying to estimate and ensure that we have only two modes. So stay in the correct shape class. And one does that by doing the search over. So here are some couple of 2D examples, and I didn't find them that my student just generated them about a week ago, so I think there's a lot more one to done. But the point is one can do this in any dimension. You just need the optimization over the diffeomorphism group for that space. So in fact, tools like LDDMM and other techniques will be useful to solve the optimization part. So we have our cost functions. We are optimizing our diffeomorphism group. We can do it in any dimension as long as we have a numerical tool for doing the optimization. So we have started doing this in 2 dimension and fitting curves from data by ensuring that we have the correct number of peaks. Okay? One sub-area of functional data analysis, of course, in statistics is probability density estimation. Probability density is a function. It's a very special kind of function, but it's a function. So one can treat it as function and do functional data analysis on it. So the original classical basic 101 statistics problem is that you have samples from a probability density, and the goal is to do the density estimation. So state of the art, non-parametric, Bayesian non-parametric perhaps, kernel methods. Okay? You put some priors on the parameters of the kernel and so on and so forth. Bayesian non-parametrics, that's the current call of the day. So we have done this in 2 different ways. The first is unconstrained. We don't think about the shape at all. Here we use the group action, which is a transitive group action. You can go from any density to any density with appropriate warping. So what we do is we make an initial guess based on some parametric family. You get the data, you assume a parametric family that's quick and dirty, fast, you get an initial guess. And of course, your original data was not from that parametric family, so it's not going to be a very good answer. But then we time warp that initial guess using this group action, and then under a maximum likelihood criteria, and enlarge the space to the space of full density. So an initial guess within a parametric family, and then as we enlarge this diffeomorphism group, we cover larger and larger points. And one can show, as long as you have a good initial guess, this can be very much more efficient than the state-of-the-art methods, because it has lots of degrees of freedom for reaching densities. So this is a paper that is going to appear soon. But the problem that relates to this talk is shape-constrained density estimation. So lots and lots of applications where you can say, I know the density is bimodal. It's like electricity consumption. It has 2 modes, high mode and low. When people are at home, electricity consumption high. People leave home, electricity consumption. So you know the density for consumption is bimodal. The traffic data. In the morning, you have peak hours. In the evening, so there are plenty of applications where you know that you expect to see a certain shape in the density. How do you ensure that the density you're estimating follows that shape constraint? So it turns out there is a huge community. There is an area called shape-constrained density estimation. It does go back to my mentor, Ulf Grenander, 1950s. He wrote the classic paper on how to estimate a density under unimodality constraint. That you know the density is unimodal, how do you estimate? So he wrote the first asymptotically efficient estimator for that. But a lot of work currently is focused on the theory of that, asymptotic, convergence rates, and so on. Since then, since 50s, over the last 50, 60 years, they still haven't progressed to a stage where if I want to estimate bimodal density, they would not know how to do it. They may do it as a mixture of Gaussians and so on, but in a non-parametric way, I want a multimodal density estimator. And so the way to do that is to use a different group action. I use the shape-preserving group action, but of course the area changes, and I want the probability density to remain a probability density, so I just divide by the area. So this is a shape-preserving and area-preserving group action, and one can show that the orbits under this group, if I apply all elements of this group, I can go from any bimodal density to any bimodal density. It fills up the whole shape class. And so if all you tell me is that I want a density which is of this shape, bimodal density, I can start as an initial guess any other bimodal density. I can just build a simple bimodal by hand and then just apply all possible warpings to reach anywhere I want to do. And we do this optimization under a maximum likelihood setup. We start from a template, we do all the time warpings, we are given the samples from a density, and by doing this we ensure that we have an MLE. Because if you want just a bimodal density, one can actually do this with a kernel estimator. You just change the bandwidth until you get a bimodal answer. So you can get a bimodal estimator, but there's by no means it's an optimal in any sense. Here what we are saying is, among all bimodal density, give me the one which has the maximum likelihood. So this is actually a maximum likelihood estimator with the shape constraint. So here are some examples. We have some, I'm not showing you the original samples, and there are these different, the student really overcrowded, but he's giving the best case scenario, the worst case scenario, the median scenarios. But these examples where we know you have a trimodal density, and these are actually estimating, that's all we know, that there are three modes. We are also playing with the heights. We are playing with the locations of the heights. And so we search over all possible trimodal densities to come up with an estimate. And there is no other multimodal density estimator in the literature, none. This is another example with the electricity data. This is some data points and a histogram. And if we impose, so this is the kernel estimator, but if we impose a bimodal constraint, it ensures that we have these spurious things don't lead to any modes. It kills out all these modes and stays in the correct density. Okay. All right on time. I want to summarize. This is more of a broader discussion, philosophical to some extent, that functional data analysis, which is very fast-growing community, which is very important in lots of different data analysis, but it almost always relies on the L2 norm and using that to compare curves, compare functions. The idea here is to focus on the shapes of the functions. Functions actually have shapes, and incorporate that information about shapes. We have a way of quantifying the shapes. One uses these different actions of the diffeomorphism groups. And instead of using functions, one wants to use shapes of the functions in doing regression, classification, and clustering, and all the other pattern analysis applications. It's much more fruitful to actually look at that, simply because, as I showed you at the very start, that a small phase variability can introduce huge amount of variance in your data if you do the standard L2 analysis for functional data. All right, thank you very much.
Thank you.
Okay, thank you very much. Two questions. The first one is how far you showed us a situation where you choose, if I understood correctly, you choose a template and just optimize the warping. Yes, we have this.
In different situations, yeah. In one case, it's just the warping. Sometimes we also add the heights as additional variables.
Okay, but then how far the choice of the template is sensitive?
Well, so there is practice and there is theory. The theory says that It's a transitive group action. You can cover the whole class. There's nothing left out by playing over the heights and by playing over the time warping. Then second part is my numerical implementation finding a global solution or it's finding a local solution? So in 1D cases, we are quite confident because 1D diffeomorphisms are much easier and we have global search methods. But the moment we start doing 2D functions and 3D functions, how to search over diffeomorphisms, certainly we have a long way to go before we can be happy.
Okay, and second question was on, you showed us this example of electric consumption alignment.
Yes.
And then you get, yes, for instance, exactly, this curve. And so what about the time axis on the bottom pictures?
Yeah, so that's a 24-hour.
What is the signification of this axis now?
Yeah, so these are 24-hour time cycles. So this is a daily profile, 1-day profile, and many profiles for different households on different days in the same month. And so there is a natural variability. Even the same household is not exactly synchronized day after day. So that's the variability. And so when we align, we take this, it goes into the program. It's just sort of like this story. It goes into the code and you get an aligned one, but you also get the phase functions. So it just separates the two variabilities. So I'm just showing you the aligned functions, but we also get the time warping functions, which went into aligning them. And so from a statistics point of view, one can include that in the analysis as an independent variable or ignore it if you think it's a complete nuisance. But the idea here is to separate shape, to extract a certain shape pattern. That's the idea. And that we do by alignment. Okay.
Thank you.
Very nice overview. I learned a lot from the descriptions of these various techniques for coming up with transformations that can mimic certain properties you want in your distribution. One property which is very much, I think, actively looked for in statistical multivariate analysis is the property of univariate Gaussian statistics. So this is the non-paranormal, John Lafferty's model, where you try to find the transformation that will effectively transform a multivariate sample into a sample that has marginal Gaussian statistics, and then you can effectively apply Gaussian methods, covariance methods, second-order moment methods to do the analysis, losing, of course, proportionately to the deviation of the joint distribution from Gaussian in terms of performance. So, but is this something that you think has?
I have not thought about it because the motivation for doing that was to analyze shape, whatever that is. Just to analyze shape and just mod out the phase variability. So most of the variations here are time warping type because you are sort of aligning the shape.
Right.
But what you're pointing to is, there's sort of another kind of a transformation one can seek, formulate it as a group action, and then optimize over that group action if you have a certain objective in mind to optimize over. But to be honest, I have not looked at it. I mean, these are mostly from the shape considerations.
Right.
Whatever the shape is.
But the density example sort of evokes this as a very, I think, interesting application of these methods.
Right. Right. Thank you. Switch it on.
Okay, thank you very much for this wonderful talk. So I have a question about you said that you want to impose some kind of constraint on the number of modes, for instance, and I think that's really important thing. But in this, I think in many of your examples, you are doing some kind of full optimization on the group of diffeomorphisms.
Yes.
And so, for instance, I do not see how you can conserve, for instance, the fact that you have just one mode, because you can, the limit you have, you can go from 2-3 modes to one mode, for instance, so you cannot capture that. And so, in a sense, how you, I think that, especially if you want to do estimation, so you have a finite number of samples, so you have some regularity issues. You have something like that. So
Yeah, let me go there.
my feeling is that there is something missing about the...
Yeah, there is something missing. That's something I haven't told. I mean, I will just go to the function, but one can talk about probabilities also, probability densities. There is always a standard regularization term. Where is it? Yeah. So I didn't mention it, but in addition to the least squares, you always have to have some regularization term to make it well defined. And one can carry that regularization term here also, and to keep it somewhat. But going back to your original question, so we have these orbits, and these orbits are representing different shape classes, but these orbits intersect at the boundary. So they are not really disjoint in some sense, and so the limiting question is there, and to the extent I have thought about it, which is not that much, is that some of these regularization penalties do help us keep away from the boundary. But I want to think more, with your help, about these orbits.
Because I think there are real issues in this. Yeah.
I agree, the issues are real. Yeah.
Okay.
But I didn't mention. I mean, whatever people do for regularization here can be brought here too. You can just add a penalty, the same penalty here, except the search space is different.
Yeah, but okay, I think there is some discussion about the fact that, okay, in some way we could have the impression that we can work in the quotient space, but in fact we cannot really do it. So we have to...
not a quotient space. Okay. I'm still working in the upper space, but I'm restricting my search to a certain orbit. And the issue is that if I start reaching towards the boundary of that orbit, then I may have some intersection with a different shape class. And so regularization is supposedly keeping me away from that, going towards the boundary. Not quotient space. I think that's real shape. This is still in the upper space.
Thank you.
Okay, let's thank again our speakers.